Okay, so Unit 2 quiz objectives 1 through 7 that we took. And try to make this a little larger. All right, so the first part, okay, very first part. We got to do a model. Now, here's what you got to understand, guys. Think about each question carefully when you do them. If you've got to make a model should include pictures and words, right? Okay, so you got to have your pictures and you got to have your descriptions. And it's saying I got to do a solid, I got to do a liquid, and a gas. All right, so solid and liquid and a gas. And we got to explain how the particles are moving. Now, solid, I mean, I could make a container or I could just put some dots all close together like this. Okay, maybe I don't want to make a container. Maybe I just do that. But I also got to make sure that I show, with all of these, what we're really focusing on is we want to show the arrangement of the particles and we want to show the proper motion of the particles. Arrangement and motion, okay? So with solids, um, my written description would just be something like vibrate back and forth slowly. All right? And so I show that with motion lines. So motion lines just look like little apostrophes around them. Okay? That's supposed to kind of show that they're just kind of vibrating back and forth. That's all. All right? Now we have a liquid. So maybe I'll make a container for the liquid. Maybe I'll even make a line that kind of gives me an idea of like a surface of a liquid if you want. I'm showing different substances. I don't have to worry about conservation of matter here. I'm just showing a gas phase, a liquid phase, and a solid phase. That's all I'm doing. So I'll just put some particles in here, but what I want them to do is I want them to look more spread out than they did in the solid. Okay? Maybe something like that. So they're more spread out. I can see that. Maybe make a note of that. More spread out. Moving a little faster. Or moving over each other. Sliding past each other. Okay? And so since they do actually change place, I'm going to make arrows. But since it's liquid, I'm not going to make real big arrows. And it's just random directions I pick. Doesn't matter what direction I pick. Just I'm kind of going random directions. Okay? There's your liquid. Gas, most spread out. Flying everywhere, something like that, I think some people put. So for this, I'm going to do like a whole box so it shows the gas enclosed. And we want these really spread out, so maybe just two of them would be good. And make big arrows. Okay? Moving fastest, maybe I put. Okay, so I was looking for particles, I was looking for the motion, the arrangement, and these models tend to be worth quite a bit when it comes to your quiz grade, all right? Like you'll have other questions maybe worth just a couple points. In the solid, they're just little like apostrophes around, quotation marks around them, okay? Because the reason why we don't do arrows with solids is because they don't change place with one another. They just vibrate back and forth, right? It's like if you guys were particles in a solid, you're moving right now, but you're not changing places with each other. You're staying in one spot, but you're moving, okay? Now, if we were to be like a liquid, you guys would get up and start walking around the room past each other and going all around each other. Just walking around the room, random directions. If you were like a gas, you'd be going around the room, random directions, but you would be running. Okay, does that make sense? Somebody say no? Okay, can I erase this, or? All right, well, number 2, when a substance is heated, what happens to its thermal energy? And I want to say more about this than actually what I was just looking for on the quiz. The quiz, what I was really looking for, I was hoping you would say something about the speed of the particles and thermal energy. So if you increase the heat of a substance, the thermal energy is going to increase, right? That makes sense, doesn't it? If the thermal energy increases, what happens to the speed of the particles? They go faster, right? Can I erase this now? Okay, so thermal energy, when a substance is heated, thermal energy will increase. And by thermal energy, you guys need to know that thermal energy relates directly to this, what we were talking about with average kinetic energy. Kinetic means moving, right? And if we're moving, we're talking about the speed of the particles, which in this case, if we're adding heat, okay, particles would speed up. So thermal energy would increase and vice versa. So if I remove heat, the thermal energy goes down. The average kinetic energy goes down. The speed of the particles goes down, meaning they're slower. And the other thing is, talking about arrangement of the particles, what else happens to them when we cool them down? They come closer together, right? More compact, all right? So that goes with number 3. Now, number 3, I have to mark these boxes like you got to get it all right. So pay attention to what it says over here. Spacing and density. Okay, so in a solid, they're closest together. And if particles are close together and they vibrate, they do. Well, what about the density then? What's that mean about density if particles are close together? Highest density, right? Okay, liquid, medium spacing, and density. Okay, the gas particles are again most spread out. And if the particles are most spread out, that means that the gas phase would have the lowest density. So you got to have both of those things for each box. If you left one off, you probably got it marked down, right? Movement and relative kinetic energy. So movement would be a vibration, vibrate slowly. And we know that particle movement, the speed of the particles relates directly to the kinetic energy. So if they're moving slowly, that would be lowest kinetic energy. Okay? Movement, sliding past each other. And so that would be medium KE, medium kinetic energy. And then the gases moving quickly or moving quickest, quickly. So they would have the highest kinetic energy. Moving energy, kinetic energy, right? So the rest of them, the last 6 boxes, are just yes, no questions. The first one's about the volume. So if we put these objects in a container, do they take the same volume as a container? Well, the particles in a solid, they just stay close together. They stay in their same shape. They just stay in their same amount of space that they take up. So no, they do not take the volume of the container. Liquid will take the shape of the container, but it won't fill up the whole space of the container. So that's a no as well. Okay, maybe I should do these together. So like solid, does it take the volume of the container? No. Does it take the shape of the container? And really I'm just looking for shape on this bottom one, okay? Does it take the shape of the container? No. Liquid, does it take the volume, the space of the container? No. Does it take the shape? Yes. Gases, do they take the volume of the container? Yeah, they're going to just be bouncing everywhere they can go, whatever's available. So if they go everywhere that's available, that means they're going to take the same volume as the container. And since the shape of the container is also space available to it, they're going to take the same shape of the container as well. So that's also a yes. All right. You will see the same diagram tomorrow. So make sure you can fill all that in. Okay, so the Celsius scale. People were able to say a lot about, like, it's based on 0 degrees being freezing point, and 100 degrees being the boiling point. Well, part of it. No. Anders? And so some people even mentioned that when it was first developed that those were backwards and stuff. But you really got to make sure that you know that this is based on the properties of a certain substance water. Water. Okay, you got that? Cool. Based on the properties of water. Based on the freezing and boiling points of water. Freezing 0, boiling 100. And then we kind of make the degrees in between. All right? Good? So let me grab that. Okay, here's one thing I want to make sure that you can tell me with kinetic molecular theory. First of all, it's just based on the idea that all substances, all matter okay, all matter contains particles that are in constant random motion. And along with that, the average kinetic energy is directly related to the temperature. We talked about this scale now, Kelvin. All right. I told you, like, what's that? Right, yeah, it's not degrees Kelvin, it's just Kelvin. And we're going to get into that more after break when we finish this stuff up. And Okay, and then 6 was the last question, right? This was a doozy. A doozy. Okay, so some things we're going to need for a model of how a thermometer works. First of all, we're going to need at least 2 pictures. Okay. Um, just thinking off the top of my head, what if we had a thermometer? We could show a thermometer being heated. Okay. Can I erase what's up there? It records my voice and my screen. Nothing else. All right, so we're gonna have to do something like just room temperature, like some kind of cooler temperature. I'm gonna need a thermometer, something like this. All right. And so particles, I'm going to need to do a couple different particles. I'm going to have to do a couple different models as well. So let's do this. And we'll do increased heat in the room maybe. Okay, and so in this example, what I'm going to have to do is I'm going to have 2 particles. I'm going to have some kind of substance in the thermometer. You could say alcohol maybe. Maybe I make alcohol green. So I'll make a key green alcohol. So that's going to be inside the thermometer. Now at room temperature, the temperature of the thermometer is going to be lower, right? So maybe I can just put some kind of mark here. And if we have increased temperature, the mark is going to be higher. Okay, now I'm showing 2 different views of the same thermometer. So we do have to be careful with conservation of matter. However many particles I put in one of those thermometers, I have to put in the same in the other one. Okay? So in the room temperature thermometer, maybe I put like 1, 2, 3, 4 of them. Okay? And I'm going to put not too big of arrows on them, but I do have to show the particles here. A lot of people just had these colored in. We always got to show those particles. And then I also need to show the particles in the air around it. So maybe we'll just make the air particles blue, something like that. Okay? And now the air around it's kind of an open system. Probably should take the temperature of a liquid or something, but whatever. Um, so at room temperature, I'm not going to worry too much about the spacing, but I do want to be careful about the motion. Okay, so draw some arrows on these, going random directions. Okay. And then for increased temperature, again, same liquid, same alcohol, so I got to do 4 particles. And so the particles are going to have to be more spread out, right? And we talked about that, the thermal expansion. And these are going to have bigger arrows. Okay? We can't forget that we got to put words on our models too to explain what I'm talking about right now. All right? And then the air in this picture, I could still do the same number of dots, whatever. Or maybe less to show that it's less dense, I don't know. Show some air around it. And the air is also going to have bigger arrows than over there. Okay? And so as the thermometer warms, what's happening is the energy is getting transferred from these particles outside. They're getting transferred to the liquid inside. They're going to have to first transfer to the glass around the liquid, but they'll eventually that energy will get transferred to the particles in the liquid. Okay, so we want to talk about in our description. We want to talk about um, particles moving slower, room temperature, and then adding heat. Added heat adds energy that is transferred to particles inside thermometer. This causes them to move faster. And spread out more, which means expand. And when they expand, they're going to expand up the tube, which means the level of the liquid inside the tube is going to get higher, which is going to correspond to a higher temperature reading on the thermometer, right? Everybody good with that? Okay, so just a couple more things I want to talk about. So on here, I also want to put down a couple things. Um, looking through our objectives as we go through this unit, talk about the air freshener, not a model, but just talking about it, the air freshener and dye demos. Right. And make sure that you understand that what's happening, whether we're talking about odor particles in the air freshener or whether we're talking about the dye particles in the beaker, in both of those scenarios, we're talking about the collisions between particles. And even in the dye demo, we also saw how temperature made those different because with particles moving more quickly in hot water, there were more collisions more often, more frequently, which caused the dye to spread more quickly. All right. Eventually, they both ended up being room temperature, which we saw like after a day or two or whatever it was, and they both looked the same because by that time, the particles were all had about the same average kinetic energy, which means they're all moving at about the same speed, which means they're all the same temperature, which means collisions are happening at the same rate in each one, and the particles are all spread out everywhere, and really the particles all together between the water and the dye are all at the same average kinetic energy as well. So moving it around in there at the same speed. Okay? If you can do solid, liquid, gas, if you can do that, then you could probably make me a model of like ice being heated and going through phases. What would the particle models look like going through phases? Okay? Make a model. Again, with models, don't forget words. Words. Describe what's going on in these pictures, okay? Um, talked about all this, all this, all this, talked about all this, talked about what gas pressure is. Okay, so this is newer stuff that we're working on with this POGO that we're going to continue working on here in a couple minutes. But gas pressure caused by collisions. And I even had you underline on your POGO where it had the read this, it said. We underlined a couple things that were important there. Collisions, sometimes we call them hits. But how often the particles hit, and with what speed or force, okay? So particles that are moving more quickly are going to hit more often, which means that they're going to have more hits. We're going to have more pressure. Okay? If we have more particles, there's going to be more hits. If we have less particles, there's going to be less hits. If we have colder particles, they're going to be moving more slowly, less hits. Okay, that's the idea that we have here. We talked about volume, the amount of space something takes up. We talked about external pressure, so not only the hits inside the container, but how do the hits outside the container affect the gas pressure inside. We talked about non-flexible and flexible containers. And the thing with flexible containers is that the internal pressure, the PI, is always equal to the external pressure, right? Do you remember that? That's key idea. Key idea, PE. The PI, the pressure internal, is equal to the PE, the pressure external. Okay? Always in a flexible container, not in a non-flexible container. That's not true. But in a flexible container, the volume can change. That's always true. The volume is going to change until those pressures are balanced out. You sure have a balloon. All right? With a flexible container. That's not true with a non-flexible container. All right? So you should know those different factors we talked about, like heat, adding more gas, the ones on your POGO that we're working on. Okay? So like what if I increase the temperature of particles in a non-flexible container, what's going to change? In a non-flexible container. So if I add more, let's say I add more gas to a non-flexible container, what's going to change? Is the volume going to change? It is? It's a non-flexible container. The volume can't change. So what's going to change? If I add more particles, what's going to change? Not the volume. The internal pressure will, yes. Okay, now I've got a flexible container and I add more gas. Now what's going to change? The volume, it's going to get bigger. But the internal pressure is not going to change. It's always going to be equal to the external. What if I have a flexible container and I cool it? A flexible container and I cool it. What will change? The volume. It'll get smaller, won't it? What if I have a non-flexible container and I cool it? What's going to change? The internal pressure. So know those ideas, all right? And then you should be good to go. I did make some questions about the dependent and controlled variables that we were doing in that table. So know what independent or manipulated variables and dependent variables are, and the controlled variables, which are the constants, the things that stay the same. Okay? The independent is what you change. Independent or manipulated, you change to test it. Dependent variable also changes, but it changes because of what you changed. All right? And so, just like the questions I was just asking. And bleep, 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 that's all.